We're going to talk about Herring's law of equal innervation. So when you have your eye movements, you want to have both eyes look at the target at the same time and with the same velocity encoding information so that both eyes can get to the target at the same time so we don't have diplopia. So if we're trying to look at this little house here and we want to look over to the left, we want the two eyes to move together, and that means we have to have co-firing of the lateral rectus muscle and the medial rectus muscle. These two muscles are connected by a neurogenic yoke, not like egg yolk, but yoke like on oxen. So the two head of ox are connected by a wooden stick called a yoke so that the two oxen will move together in the same direction at the same speed. So the medial rectus muscle on one side is yoked to the lateral rectus muscle on the LOI. And that neurogenic connection, the yoke, means that both muscles will receive the same innervation, and that is called Herring's law of equal innervation. Simultaneous to that, we have to turn off the antagonists. So in this case, the lateral rectus muscle in this right eye has to be turned off when we fire the medial rectus muscle in the same eye. Otherwise, you'll have the eye fighting against itself. So we have to have equal innervation, Herring's law, and we have to have reciprocal disinnervation, reduced innervational effort, and that's called Sherrington's law. So we reduce the innervation to the antagonist, and we increase the innervation to the agonist muscles, who are yoke muscles. The reason this is important is sometimes the yoke is what's creating the problem in the misalignment of the two eyes. So for example, in this H diagram where we have the motility represented, if you have a right superior oblique palsy, so the superior oblique muscle in this case is decreased, we'll have overaction of the superior oblique muscle on the right's antagonist. So its antagonist is the inferior oblique muscle. So the inferior oblique will appear to overact because the superior oblique muscle is weak, and so when your direct antagonist is weak, you will look like you're overacting. And that overaction means that this eye is actually already looking at the target. So when we ask this eye to also look at the target, it'll appear that this left side superior rectus muscle is underacting because the innervational effort needed to drive the right eye to the target is less than it would have been had the superior oblique not been weak. Because the superior oblique on the right is weak, the right inferior oblique is overacting, it receives less innervation to look at the target, and that is transmitted to its yoke muscle, the superior rectus muscle on the left side. In order to remove this disparity and resolve that this is a pseudoparesis, we're going to block this right eye. And when we block it, we can't see the target anymore, and this underacting superior rectus muscle on the left will now move up and be able to see the target, proving that the left superior rectus muscle underaction was from Herring's law. And there's nothing wrong with that left superior rectus muscle. That is a pseudoparesis. Pseudo means false. So it just appears to underact because its yoke muscle is overacting. Its yoke muscle is overacting because its antagonist muscle is underacting. And over time, what that means is the deviation will spread around because each muscle will now transmit by Herring's law to the other muscles. And that will cause the deviation to become comitant over time. Comitant means the same in all directions. So over time, a long-standing deviation will be the same in all positions of gaze because underacting muscle leads to overaction of its antagonist, leads to underaction of its yoke muscle, and round we go until the whole deviation becomes comitant over time. So many deviations come to us, and where are long-standing, are comitant because of Herring's law.